when I looked at the program, good that I did, I realized that I had been invited to give a talk on this subject. So that's what I'm going to try to do. It's a bit embarrassing because, of course, I have nothing new to say, and whatever little I know from the way to present it, I all learn from people in the room, like Detlef, Shelley, and Nino, and also Tim Maudlin. Anyway, so let me start by reminding you of the classical view of probabilities. If laws are deterministic, then probabilities, the use of probabilities, are only due to our ignorance. That was stated by Laplace in many ways, but I like the way he says it here. The curve described by a single molecule in air or vapor is regulated in a matter just as certain as the planetary orbits. The only difference between them is that which comes from our ignorance. Probability is relative in part to this ignorance, in part to our knowledge. I didn't prepare this talk, this quote, for the purpose I'm using it now, but that's an example, by the way, of what people call beables and ontology. Laplace had an ontology. He thought there were molecules, even though we didn't know them. And then he also had an epistemology, if you wish, namely he had a probability distribution, or use probabilities, or in modern classical statistical mechanics, that led to the probability statistical mechanics, where you have a probability, but the probability is not a complete description of the system, because the particles have, classically at least, their position and velocities and so on. And that's a good example of the distinction, why people insist that there should be something that we talk about without ever necessarily describing it in every detail. Now, what about quantum mechanics? In quantum mechanics, psi square has a probabilistic interpretation, as we all know. But then you could say, is it only ignorance? Is it reflecting only our absence of knowledge of the system? And then, of course, an immediate question is, why does it evolve according to a physical law? Classical probabilities don't necessarily evolve according to physical laws. They may depend on our information. And the other thing is, what about the reduction or collapse of psi during a measurement? Is that simply related to the fact that we learn something about the system? Sometimes people like to think of it in a way that, you know, we reduce the wave function because we have learned something. The wave function represents our knowledge of the system, and therefore, if we learn something, we of course change, just like we do with classical probabilities. So let me start with a, okay, I know my talk's about non-locality, but so let me start with an example which will already pose the question of non-locality, and that's Einstein's boxes, which is an example which is actually classical, but not all that well known. At least I didn't know it until a few years ago. And you have a particle in a box B, and you have a single particle. You cut the box in two, and then you call B1 and B2 the two parts, and you send them far away. So a single particle, and then the state is indicated by B, meaning the particle is uniformly in B. And then it becomes a superposition of B1 and B2, where B1 or B2 means that the particle is in box Bi. I put is in quotation mark because quantum mechanics is ambiguous. And that's what we are going to come to. Does it say it is in the box, or it is found in the box if we measure it? That's not the same statement, unless you think, I mean, a priori it's not the same statement, and we get to that in a minute. So the two boxes now are separated and sent as far apart as one wants. They say one is in Tokyo and the other in New York. Let's not go further than that. If you open one of the boxes and you don't find the particle, then you know that it is in the second box. Therefore, the state collapses instantaneously and in a non-local way. Because, you know, the wave function, there is a wave function in New York, another one in Tokyo. You open one of the boxes, you see there's nothing, then you know it's in the other box. Of course, that's not surprising classically, but quantum mechanically, it means that the state is collapsed into B2. And of course, if you open the box B2, you will find the particle. There's no doubt about that. But now you can ask the question, is the reduction of the wave packet in that example, of the state vector, a real operation, or does it represent simply our knowledge? Is it epistemic, like in the classical view? The classical view, you could throw a coin, and then you don't look at the coin, and then you don't know it's half and half, and then you look, and then you know which one it is. Is it the same thing? Well, now we come to a dilemma, and the dilemma is very important. If it's a physical operation, if the wave function, the state is somehow physical, it's not just our knowledge of the system, then a non-local form of causality exists. There is a sort of an action at a distance because you have, you know, acted on only in one box. You don't open the other box. You open one box, and then you collapse the state, and the particle is in the other box. So if you have changed something physically, you have done it in a non-local way, period. If not, I will come to your question. Let me finish my sentence. If it's epistemic, then by definition, it means that quantum mechanics is incomplete. That's what we, and starting with Einstein, who say it's incomplete, mean. That's all we mean. We just mean there are other variables than the wave function, namely one variable tells you it's in one box, and the variable tells you it's in another box. Okay? And these variables, which tell in which, for example, the position of the particle will tell you if there is a position. But if there is a position, then it's incomplete because there is a position on top of that. But that's not different from Laplace saying, of course, the probability that we assign to molecules is not the complete description because on top of the probability, the particles have actually a position. Okay, now I want to put aside the issue of completeness. In Bohmian mechanics, for example, the particle always has a position, and therefore it's always in one of the two boxes, and there's no non-locality whatsoever in this example. But if, for example, in GRW with matter density, there will be half of the matter there, half of the matter there, and by opening one box, you might collapse it into the other, and there will be some non-local action. Yes?
I don't quite know why you call this non-local, because even under ordinary Schrödinger time evolution, the spreading of the wave function can be arbitrarily rapid, and it doesn't present any problems with Einstein causality.
Okay, let's forget about Einstein causality. We're just saying, I wasn't even speaking about Einstein causality, I wasn't speaking about the wave function, I was speaking about the reduction, and I was just posing a dilemma. Either we learn something of the system, which by definition means there are other variables that characterize the state, that's our definition, we should at least be allowed to have that definition, or there's something physical going on, and then there is some action at a distance, and no, but now you're telling me there is another sort of action at a distance coming from the spreading of the solution of the Schrödinger equation. Okay, maybe. That's not what I'm talking about. That's all. I haven't said there is a problem with relativity. I haven't said anything. I've just said this dilemma. Now I want to put aside the issue of completeness because in Bohmian mechanics, the operation in Bohmian mechanics would be epistemic in this case. So let me try to explain what is non-locality and why it's the non-locality I want to discuss. I want to discuss a causality, which is not a mere correlation, which has the properties of being instantaneous. By opening one box, you collapse the state in the other box. And I want to show that there is some non-locality in the world, not in that example, but using some other example. It goes arbitrarily far, meaning, it could be New York and Tokyo, but it could be the moon and the earth or anything you want in the universe. And the effect does not decrease with the distance because the effect is basically either you're a particle or no particle. It's yes, no. It's not something which decreases like gravitational force. And it doesn't decrease with the distance like, for example, the effect, the heat kernel or the kernel of the Schrödinger equation. It's individuated, which is a property which will be clear later, but it means that it has to do with that box and that box, which are coming from a common box, okay? It's nothing to do, there is no action at a distance or no force acting between one box and some other box which had nothing to do with the first box to start with. So you have to, it's individuated, and action at a distance can be sent to transmit messages. Let me explain what I mean. In gravitation, in Newton's gravitation, you have the property 1, 2a, but not b, because it decreases with the distance. But in principle, if I move my arm, I affect the movement of every body in the universe instantaneously, and it goes arbitrarily far, but of course it decreases with the distance, and the effect is barely noticeable. And it's not individuated, because everybody is affected in the same way. And of course, that could be used to transmit messages in the sense that I could either move my arm or not move my arm, and if you can detect the effect, then you can send a message by coding it in a sequence of zeros and 1 and correlating the zeros and 1 with the movement of my arms. But the post-Newtonian physics field theories try to keep 2a and 4, but not 1. So it tries to propagate at finite speed. The question is, in quantum mechanics, what I'm claiming is there is a phenomenon with properties 1, 3, but not 4, which is usually used for pseudoscientific reason, but you can have the properties 1, 3. That's what I want to demonstrate. So now comes the punchline. If you agree with this, you agree with the rest. Listen to that. So we have two people, let's say, Tim and I, and we exit the room by 2 different doors. There are 2 doors. That's X and Y. And when we reach the door A and B, somebody asks us a question. The question is just a number. It's not what is your age or something like that. It's just a number, 1, 2, 3. Somebody says 1, 2, 3. And we have to answer yes or no. It's a game. It's a silly game. Okay? So we have to answer yes and no. And Tim and I can talk to each other, decide what to do. We go to the door. Somebody asks a question, then we answer. Then we come back. We repeat the experiment 1,000,000 times or 1,000,000,000 times. It's boring, but we do it. Okay? And now we look at the statistics of the answer. The questions vary. Sometimes it's 1, 2, 3. And the answers vary. It's yes, no, etc. But then we notice something strange. And that's the main point. When the same questions are asked at both doors, A and B, we always get the same answer. Now it's very trivial to do. I mean, you know, Tim and I agree on each run of the experiment. Before leaving, we agree on a strategy. We say, look, if it's question 1, we both say yes. If it's 2, we both say no. And if it's 3, we both say yes. If we agree on a strategy, there's no problem. Okay? We can give the result. Or we could have a telephone, and when one person reached the door, he says, I question 1, and I gave the answer yes. Then the other person says, okay, now I have question 2 and 3, then I do what I want. And if I have question 1, I also yes. Then I'm sure that whatever the question will be, the answer will be the same. Okay? I claim, and I've never heard anybody giving me another answer, I claim that these are the only possibilities. Either the answers are predetermined, or there exists a form of causality at a distance after one asks the question. By causality at a distance, I mean the telephone. I mean, that doesn't go faster than light. There's no problem at that moment. Okay? Of course, if you are told that the questions are simultaneous in a reference frame of the room, in a sense that there couldn't be any transmission of information, or transmission even, you know, that wouldn't go faster than light, then you would have a problem, which is, of course, what happens. But a priori, my point is simply that you have to pause. I have no time to make a poll, but you have a question? No, but you have to pause and ask yourself, what is the third answer? Do I have a third answer? That's all. I don't see any third answer.
There could be a conspiracy.
Yes, that's true. There could be a conspiracy in the sense, yeah, that's good. You could say, well, it's just random. You know, I throw a coin and it comes always head every time, okay? And I do it, okay. There could be a conspiracy in that sense. It could be just, that's just saying, well, these are perfect correlations in the world that are reproducible. You can do it today in Bielefeld, tomorrow in Paris, etc. You can reproduce them. Let's say you redo the experiment with not only Tim and I, but 2 other people, and it's perfectly reproducible. And there are zillions of experiments where it works, but nevertheless, we say there is no explanation to this correlation. That would be a way to give up science, because of course I could also say that the moon being there, because I think the moon is there, but you know, being there at a certain place where it's supposed to be according to astronomy is just a coincidence, and there is no need to account in it for any way, and that could be done for evolution, for any part of science. I could just say it's a coincidence that there are fossils, for example. I could deny the theory of evolution and say fossils is just a coincidence, for example. You could do that for any part of science.
The non-local effect might be of such a form that it wouldn't be appropriate to think of it in terms of causality. It might be totally symmetric. There would be other side.
Yes. Yeah. Okay. There is a problem. Okay. But look, I suggest the following. I want to show that there is something which is, you see, I'm saying that there has to be a communication between the 2 wings of the experiment, between the 2 doors, some form of communication. What is going on exactly, that I leave to the next speakers who will speak about relativity and GRW and Bohm. I decided not to go into the issue of relativity. I'm just describing what seems to be the 2 possibilities. Okay, and I want to say that this argument, stated the way I do, which is not the original one at all, but that's the Einstein-Podolsky-Rosen argument in Bohm's formulation. Einstein-Podolsky-Rosen said either there is a communication or the quantities are predetermined, and if they are predetermined, that means the quantum mechanics is not complete, just the same way as I said, if the particle is in one of the two boxes, then quantum mechanics is not complete. There is some other variable, which misnomer one calls hidden variable, but you have to introduce variable if you want to pretend that there is no communication. The problem is that this assumption, alone leads to a contradiction when observations are made when the questions are different. Now let's look at the statistics when the questions are different, not the same. Because you could also say, well, let's look at the statistics when question 1 is asked there and question 2 is asked there. They're also reliable statistics. And so we are going to show that that leads to contradiction, and that argument, in essence, but it was much simplified by, Dürr, Goldstein, and Zengi, but it was in Maudlin, and there are several versions, but the original one goes to Bell 1964, and as you notice, there have been almost 30 years between the two, and I think it's fair to say that most misunderstanding of Bell comes from the fact that people have forgotten the EPR argument of 35, or thought, even worse, that Bohr replied to it. So the proof that it's inconsistent is simply, it's very, very simple, so I'll give it. There are 3 questions and 2 answers. So if the answers are given in advance, there are only 8 possibilities. Yes, 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 no, etc. I don't need to list all the possibilities. It's pretty clear, okay? So now, Tim and I could decide, for example, that in every run, we are going to take this choice, no, no, yes. Or we can take a uniform distribution of all the 8 runs. Or we could take only this one and this one. Or make any choice we want of strategies when we repeat the experiment a million times. The fact is that in each case, there are at least 2 questions with the same answer. Okay? So whatever distribution we choose when we repeat the experiment a million times, the frequency of the answer to 1 equals the answer to 2, plus the frequency of the answer to 2 equal answer to 3, plus the frequency of the answer to 3 equal to answer to 1 must be bigger than or equal to 1. The sum of the frequency. I'm talking about frequency. I want even to introduce probability. It's just a fact because, if we choose, for example, always this strategy, then we always have 1 equal 2. So it's 1. If we took this strategy and this one, then we always have either 1 equal 2 or 1 equal 3, and therefore the frequency is always 1. Could be bigger than 1 if by chance we sometimes take this one or sometimes take this one, because then, of course, all the answers are the same. Otherwise, it's exactly 1. If we exclude those 2 guys, then it's always going to be 1, the sum. It's always 1. But there are some experiments, which I could do actually with human beings. I could do it with Tim if we set up things right, where the frequency of the answer to 1 equal the frequency of the answer to 2 is equal to the other one, and they are symmetric, but they're all equal to 1/4. And now 3/4, that implies that 3/4 must be bigger than 1, which I agree with all. That's maybe the only thing we'll all agree in the conference that's false. Okay? I should say that this part of the talk is not just 3/4 bigger than 1, which is uncontroversial. I think this is the part of the foundation of quantum mechanics which should be uncontroversial, although it's not. But everything else, I think even Bohm theory is more open to discussion, but this is not so. So when you get the point, that's Bell, and that's the end, because that shows that the answers can't be predetermined. Now I'm going to quote a physicist, who is not Bell, because usually when people like me are accused to do philosophy, then we like to quote a physicist, but it's always Bell. So people say, well, but Bell is an exception. So I'm going to quote a famous physicist who derived essentially the same inequality without apparently realizing what had been done by other people. But here is what he says. That's all. That's the difficulty. That's why quantum mechanics can't seem to be imitable by local classical computer. By that he means things by works only by local correlation, local causality. I've entertained myself always by squeezing the difficulty of quantum mechanics into a smaller and smaller place, so as to get more and more worried about this particular item. It seems to be almost ridiculous that he squeeze it to a numerical question that one thing is bigger than another, that 3/4 is less than 1. And that's Feynman. Okay? So at least Feynman, rediscovered these things independently. Now, let me briefly describe experiments, and then let me describe the quantum. People will say, well, quantum mechanics explains that. Well, let me go back to quantum mechanics. But first, let me describe the experiment in a way which is due to David Mermin, but it's sort of a funny way. But it's important to realize that it really doesn't matter what the experiment is. What matters are the data. we have this correlation, which is 1/4 when the questions are not the same, and equal to 1 when the questions are the same. And we have to account for that, and there's no way to account for that without assuming that there is something going on between the wings of the experiment. What exactly goes on, that depends on a further theory. But the point is this: you have something that sends, well, maybe particle if you like to a particle, it sends something to here a measuring device which has 3 positions, 1, 2, 3, and the other has also 1, 2, 3, there is on 3, there is on 2. So here is question 2, there is question 3. And then there are 2 lights which you don't see in the color, but either is the green light or the red light that flashes as a response. So the green and the red is like yes and no, and you repeat the experiment millions of times. And here is a run of the result. So you see, in dark, I have 2, 2, GG, green, green, 3, 3, here I have 2, 2, red, red, etc. Each time I get the same questions, I get the same answer. Of course, sometimes red, sometimes green, but both the same. Okay? So it's completely, it looks completely random, but they have this perfect correlation. And now I've underlined the case where you ask different questions and you get the same answer. Like, for example, there you have 2 and 3 and red, red. Okay, and you find something like 35 out of 130, which is not quite a quarter, but it's sufficiently less than a third to make a difference with what it should be, because 3 times that should be bigger than 1, according to. Okay, so that's it. That's the experiment. And now the question is, I mean, suppose I give you those data, and I tell you, you know, the experimental setup is that. Don't care what the details are. Now tell me how you account for that without assuming that there's something going on between this experiment, this part of the experiment, this one. Something. I'm not sure what, but something must go on because the predetermination doesn't work. Okay? So now I can come to quantum description. But the problem of the quantum description is that it's sort of misleading, because the problem has really to do with the statistics, not with the quantum description. I don't care about quantum mechanics. Quantum mechanics go throughout of the window. The statistics will still be there in a million years, even if quantum mechanics is replaced by a deeper theory, I don't know what. You see, so you will still have to account for this non-locality. I mean, that's why it's so deep about the non-locality, is that it's something which is going to stay even after quantum mechanics has disappeared and replaced by something else, if it ever happens. But the quantum description is this. X and Y are, of course, particles. A and B are Stern-Gerlach apparatuses that measure the spin along some direction. I put measure the spin in quotation mark because exactly for the reason which are indicated here, there is no real measurement of something pre-existing to the measurement. So you are not, that was my objection this morning to Pierre Hornberg's talk, you are not really measuring something because there is no property of the system which is the spin in those directions. But anyway, the state, the quantum state of the particle, 1, 2, 3 are directions for this measurement, and what we call yes, no are up and down. So the state is the famous entangled state. At A, you have in the direction 1 it's up, and B in the direction 1 is down, minus the opposite for A and B in direction 1, and the same thing in direction 2, same thing in direction 3. This is rotational invariant, so you can take any 3 directions you want, and it will always be the same form. That's just a mathematical fact. That's nothing deep. And so what happens? If you take the state of the 2 particles, it's something like this. If you measure the spin direction 1 at A, and you see up, the state becomes, that's a collapsed state, it becomes only this part. Exactly like with the boxes. You collapse, you see the particle in one box, or you don't see it, then you collapse the state. If you see down, then the state will become this, and B1 will be up. There, B1 will be down. Similar result if you measure the spin in direction 2 or 3. But then the state changes non-locally at B. It changes non-locally because B, you see, the 2 wings there could be arbitrarily far. So if I measure something here, I change the state over there. And now we can have the same dilemma as for Einstein boxes. Is the reduction of the state a physical or an epistemic process? If it's physical, then we have non-locality. We have a form of non-locality because we are changing the physical state of the universe far away. If it's epistemic, then we are back to square one. That's what most, I mean, people usually oscillate when they discuss this thing between the 2 answers. You have to stick to one of them. If you say it's epistemic, then you have to know what it means. It means that the answers are given in advance. You learn what the answer is. So the answer is given in advance, which means that the particle at B was up in the 1 direction or down, or up in the 2 direction or down the 2 direction, or same thing in 3. It was one of the the three possibility, or the two possibility in each of the three cases before any measurements at A. Because the measurement at A is not supposed to cause anything at B, and the result at B, then you have to explain this perfect correlation. But Bell shows that this leads to a contradiction when the observations are made when the directions are different. That's what we just went through. So the perfect correlation, here you notice that it's perfect anti-correlation. If it's up here, it's down there. But that's just a way to say that if it's up, I say yes here, and if it's down there, I say yes. I mean, that's just a choice of convention, are not merely correlations, but the result of a subtle form of non-locality. In other words, the reduction of the quantum state, which is non-local, is not merely epistemic, but relates to something physical. What it is exactly, that we can discuss. Okay, now people use this, but you can't use that to send messages. Okay. Maybe that's true, but that doesn't mean that it's harmless. If one could, of course, that would be a big problem. But the point is that each side sees a perfectly random sequence of red and green. If you remember the slide I've shown there, each side has a perfectly random sequence of red and green, whatever the measurements are. That's true. But if each person tells the other which measurement they have made, 1, 2, 3, without telling the result, you just say I measure 1 and then 2 and then 3, etc., etc. Then they both know which result has been obtained on the other side when the same measurement is made on both sides. So if the person there asks the question 1, 2, 3 and gives a list and then sends by telephone to the other person the list that they've made, and if they are sufficiently random, there'll be some coincidence where the question here was 1 and the other there was 1 or 2 and 2, and then the person there knows the answer on the other side without having ever been told what the answer is, because it's enough to look at his own answer. So they have a common sequence now. They share a common sequence of yes, no, and that's the basics, if you wish, of quantum information, cryptography, and so on, or red-green, which is some form of information. They have a joint information. Since the information cannot possibly come from the source, which is what Bell showed, some sort of non-local transmission of information has taken place. Bell was quite explicit about what that means. Let me finish by going into the history. So Bell said this. Let me summarize the logic that leads to the impasse. The EPR-B, EPR being Einstein-Podolsky-Rosen and B being Bohm for the reformulation of the thing, correlation are such that the result of the experiment on one side immediately foretells that on the other, whenever the analyzers, the questions, if you wish, happen to be parallel. Parallel means whenever the same questions are asked. If we do not accept the intervention on one side as a causal influence on the other, we seem obliged to admit that that's too weak. We are obliged to admit that the result on both sides are determined in advance anyway, independently of the intervention on the other side, by signals from the source and by the local magnet settings. But this has implications for non-parallel settings, which conflicts with those of quantum mechanics. So we cannot dismiss intervention on one side as a causal influence on the other. He was very explicit about his own result, which is almost universally misunderstood. It's always misunderstood as showing that there are no hidden variables. So everybody says they're happy. I learned that as a student, can be happy that there are no hidden variables, meaning the values, the predetermined values don't exist, which is exactly true. That's Bell showed. But Bell, of course, knew that EPR had showed that if the world is local, then those variables must exist. That's the first part of the argument. He knew it, he repeated it, and was uniformly forgotten, except by Feynman. But Gell-Mann, for example, said some theoretical work of Bell revealed that the EPR-B experimental setup could be used to distinguish quantum mechanics from hypothetical hidden variable theories. After the publication of Bell's work, various teams of experimental physicists carried out the EPR-B experiment. The result was eagerly awaited, although virtually all physicists were betting on the correction of quantum mechanics, which was in fact vindicated by the outcome. So here he's very clearly stating that the competition is between quantum mechanics and hidden variable theories, which I'm not sure what he has in mind, but what he means is that with the idea that these variables are predetermined in this case. And he's right. It's important to emphasize for everybody that us, Bohmians, who are the bad guys who believe in hidden variable, do not believe in hidden variable. We know that there are no hidden variable in that sense. We know that the spin values don't pre-exist to the measurement. We explain that the measurement produces the result of spin, and they produce the result of momenta and energy and all these other observable except position. So it's important that we have no problem with that. But of course, the EPR part says, how do you explain the correlation? You could ask Mr. Gell-Mann, how do you explain the perfect correlation if they are not predetermined and there is no form of action at a distance? There's even more surprising quote. There was a talk by Bell with this picture that was in France, and it's called Boltzmann's Socks and the Nature of Reality. And Boltzmann is, I don't know, he was a scientist at CERN who was wearing socks of different color. So if you saw a sock which was pink, then you knew the other was not pink. That's like knowing things, but of course the color of the socks, they are presumably there when Mr. Boltzmann gets dressed in the morning, so you know, they are there before you look. And of course they are perfectly correlated, or if you wish, anti-correlated, the socks, pink, not pink, but nevertheless there is no mystery, and that was the point of Bell. The point of Bell was to say there is no mystery in the socks. But then the whole article was saying that reality is not like that. Photons and electrons and so on don't behave like the socks because there is no color put in advance. Yeah, I'm almost done. And Gell-Mann says the situation is like that of Boltzmann's socks, described by John Bell in one of his papers. Boltzmann is a mathematician who always wears one pink and one green sock. If you just see one of the feet and spot a green sock, you know immediately that the other feet sports a pink sock. Yet no signal is propagated from one foot to the other. Likewise, no signal passes from one photon to the other in the experiment that confirms quantum mechanics. No action at a distance takes place. Well, that's a bit complicated, and I refer to you to the book by Tim Maudlin on non-locality and relativity to disentangle all these statements. But the point of the article by Bell, I don't know if you read it, but the point is that it's not like Boltzmann's socks. That's the point of the article called Boltzmann's socks. I mean, that's not, now this is not even a statement about physics, it's a statement about literature. I mean, if you read the paper, then you see that that's what he says. He may be wrong. Gell-Mann could say he doesn't agree with Bell. But the problem is that many people say, I agree with Bell, and then they say, they claim that Bell has shown exactly the opposite. I mean, for example, I was brought up with the idea that Bell has shown that Bohm's theory, I mean, it wasn't even mentioned, but the implied that Bohm theory is impossible. And when you read speakable and unspeakable, you see defense Bohm theory from beginning to end. I was absolutely baffled when I got hold of the book many years ago, the speakable. I read it almost without lifting my eyes because I was fascinated that the guy was saying exactly the opposite of what everybody else says he's saying. And this is again about literature, not about physics. Then Wigner, of course, makes a similar statement. He speaks of a proof by von Neumann, who was trying to prove that these bad hidden variables can't exist. And he says, though it was more convincing later by Koch and Specker, still uses assumptions which can quite reasonably be questioned. In my opinion, the most convincing argument was presented by Bell. More surprising is David Mermin, who actually wrote a very clear and very good article on the two theorems of John Bell in Reviews of Modern Physics, but he says the following. Bell's theorem establishes that the value assigned to an observable must depend on the complete experimental arrangement under which it is measured, even when two arrangements differ only far from the region in which the value is ascertained. So he's saying that if the spin here is something, then it depends on what the arrangement is far away. A fact that Bohm theory exemplifies, and that is now understood to be an unavoidable feature of any hidden variable theory. To those whom non-locality is anathema, Bell's theorem finally spelled the death of the hidden variable program. And again, that ignores the EPR part of the argument, which I put in the beginning. Einstein was also misunderstood, by the way, because people always say, oh, Bohr refuted Einstein. But in fact, if you go back to the, well, that's in 48, but if you go back to the 1935 paper, you can see that most people did not understand what Einstein said. And here is a summary from the book, the Schlipp book, about the Einstein philosopher, the essential scientist philosopher. An essential aspect of this arrangement of things, which are previous physical objects in physics, is that they lay claim at a certain time to an existence independent of one another, provided these objects are situated in different parts of space. The following idea characterizes the relative independence of objects far away in space, far apart in space. External influence on A has no direct influence on B. That's exactly the statement of locality. And then Born rephrased it like that. Listen to the difference. The root of the difference between Einstein and me was the axiom that events which happen in different places A and B are independent of one another, in the sense that an observation of the state of affairs at B cannot teach us anything about the state of affairs at A. But that's, of course, absurd. I mean, if I take a picture, I cut it in two, I put the two half picture in an envelope, send one envelope to New York, the other to Tokyo, then if somebody opens one envelope, he knows immediately what is on the other envelope. It's like the socks. There is nothing mysterious to that. It's unbelievable that he could assign to Einstein such an absurd view, because, of course, Einstein couldn't possibly think something so absurd. And it's quite different because he's speaking about influence, not teaching us anything. That's the point. Okay? Mermin, in his better moment, made the following classification. So now you can ask yourself, which classification do you fit into? Contemporary physicists come in two varieties. Type 1 physicists are bothered by EPR and Bell's theorem. Type 2, the majority are not. But one has to distinguish two sub-varieties. So first, ask yourself, you are one or two. Type 2A physicists explain why they are not bothered. Their explanation tend either to miss the point entirely, like Born's to Einstein, that's the previous slide, or to contain physical assertions that can be shown to be false. Type 2B are not bothered and refuse to explain why. Their position is unassailable. There is a variant of type 2B who say that Bohr straightened out the whole business but refuse to explain how. And now I'm finishing with a quote which is again literary, and I'm happy that nobody else used it today in this conference, the Tolstoy quote. I know that most men, including those at ease with problems of the highest complexity, can seldom accept even the simplest and most obvious truth, if it be such as would oblige them to admit the falsity of conclusion which they have delighted in explaining to colleagues, which they have proudly taught to others, and which they have woven thread by thread into the fabric of their lives. Thank you.
That you have projected, I would have added 2 or 3. For instance, the people who call into play also realism.
Yeah, but yeah.
You could have put Zeilinger and even a spec. What Bell theorem proves is that you must give up either locality or realism.
Yeah, but that's of course
absolute nonsense.
Yeah, but that's of course. You see, yeah, that's true. You see, what people, okay, let me explain for everybody what the comment means about realism. Realism means exactly this, that there are these predetermined values. I mean, that the spin is real before you measure it. But of course, we have been explaining that you can't explain this perfect correlation without assuming that, unless you assume that there is a certain form of, non-local causality. That's all we are saying. I mean, so, people say, the problem is that the 35 argument, the 1964 argument of Bell just does that. But Bell knew EPR, but Bell is, Bell is way over his readers. That's my problem with Bell. He's much too clever, and therefore he's clear, but he writes for an audience, which, of course, myself, when I read Boltzmann Socks when I was 20 years old, I missed the point. So I think I can, but I'm not Gell-Mann, but I can understand that people miss the point. I mean, it's not so, it's very briefly stated, and you have to really understand. I mean, I don't find him so easy to understand. And of course, he does summarize EPR argument, does repeat it, but sometimes in footnotes and so on. And it seems to me that, people limit themselves to 64, then they're right. But if you forget the 35, then you miss half of the argument. Well, I don't know. Oh, there it is. There is somebody.
Now is the conclusion that we should be bothered by EPR and Bell.
Yes.
And if we are bothered, what do we do with this bothersome? Will we carry it along for the rest of our lives? Or,
well,
I'm lacking sort of an understanding of what the message is.
Well, there is a theory. the Bohm's theory in 1952, which of course introduces explicit elements of non-locality in it, and that's usually regarded as an argument against it, and you usually say, oh, hidden variables are impossible, etc. I regard it as an argument for Bohm's theory, because any theory about the world must respect this non-locality, and Bohm explains how it is because of the wave function guiding the particle, and they guide it in a non-local way. But then, of course, an obvious objection is how do you make this thing relativistic? And the answer to that is in the next talk. Or what do you do with relativity? But of course, it is a concern about relativity, which is deeper than any other that I know. But that doesn't mean, as I said, these will be the two next talks, so I don't want to, take the time of the next speaker to give the answer. But of course, the logic for me is that, there was a big defect in Bohm's theory that uses non-local. We don't want that. And Bell was bothered by that aspect of Bohm, and by thinking about it and asking, is that an unavoidable feature of quantum mechanics, as he says, that these are his words, then he found that it is. And he found a proof of that. A proof which is deeper than Bohm, Bell, GRW, whatever, which will remain forever, this result, because it's just based on, unless we found by accident that the experiments were badly done or something like that, but, that would be a miracle. That's something rock solid in foundation of quantum mechanics, and of course we should be bothered, but of course it changes the value judgment we have on Bohm from negative to positive to highly positive, because it also GRW, of course, is non-local. But everything that incorporates the wave function, takes it seriously, not as information, has to have this non-local aspect. Yeah, there is something there.
Right, we have 2 or maximum 3 comments.
There is Sorkin and Hohenberg and him.
Just a quick comment. A few years ago, we were refuted a paper in Physical Review because Bohm's theory is refuted by Bell's theory and so on. So,
I was not the referee.
Obviously. A number of years later, we were refuted a paper because Bohm's theory is completely equivalent to quantum mechanics, and therefore they can bring nothing new. So this shows, well, how things change and evolve sometimes, but in my opinion, they show also the duty of our community here to convey all those things that you spoke about to a larger community of people in physics that obviously don't know them well.
Yeah. I'm trying to do that all the time.
Thank you.
Good comment. Thank you.
So one thing one can notice is that in the Feynman quote, he refers to a classical computer in that quote.
Well,
and I just wanted to say that in both EPR and the various proofs of Bell's theorem, there is an underlying classical ontology. And that's the claim I make. And in the quantum ontology, you cannot formulate local causality. Now, we're not going to solve that here, but that is the claim that I make, and I'd be happy to discuss it with you. There is the EPR, as clarified by Einstein's later comments, talks about the separability principle, which is a classical notion, and which is not something that is consistent with the Hilbert space ontology.
Okay, my only reply to that is that I haven't spoken about Hilbert space, and I haven't spoken up until the end when I explained the quantum mechanical description. I've only spoken about data. I could do the data with Tim. I mean, if we had the right magnets and everything, and the EPR, the Stern-Gerlach apparatus with us, we could just reproduce those answers to those questions. You go there and you ask questions, and somebody else goes ask questions, and we give you these statistics, and then you explain us these statistics. That's all. And it's not so easy to explain. It's not a question of ontology. I haven't talked about ontology except flashes, which are green. I mean, not the.
I'm sorry. Bell's theorem says that any theory that obeys local causality violates quantum mechanics.
Yeah, but EPR.
Any theory. So we're talking about theories. Bell's theorem is about theories. You can't say it's not about data. It's about theories. I mean,
right.
But I did not.
I'm sorry.
I just wanted to say that.
I did not. Okay, Pierre. Then the point is that I did not explain Bell's theorem.
I'm sorry.
I explained Bricmont's theorem, if you wish. Okay. I mean, call it another name. But what I explained today had nothing to do with Bell's theorem. It was not presented the usual way. It's not due to me, it's due to Dürr, Goldstein, and Zangi, I think, the paper I'm basing myself on. Let's call them their theorem, the DGZ theorem. But the way I presented it has nothing to do with the usual Bell's theorem.